All right, got actually asked several questions. These are for the Organic 2 homework, and as always, with the preface, we are in biochemistry, and this is definitely not my wheelhouse. So, first question here is on question 12. It wants to know the alpha and beta pyranized form of D-galactose with methanol in the presence of hydrogen chloride. So, just a kind of quick reminder, well, first thing we're going to do is going to cheat. You do not need to know like what the sugars are, like glucose, sucrose, any of that. That's more of a biochemistry thing. So the homework's here just because you can go look this up. So we've looked at galactose. Oh, I told you to search for. So look at D-galactose. It's going to be this structure here. So we're going to end up having this OH group attack this oxygen. So let me draw it here in ACD Chem Sketch. Ooh, no good way to draw this in Chem Sketch. Okay, so when we get done, what we're looking for is a ring where we've got two oxygens on one side, two oxygens on the other, and the choice of whether or not it's an alpha or beta is based on where this OH group is relative to the oxygen. So when this loops around, this oxygen here attacks this oxygen. If the OH group is up, it's a beta form. If it's down, it's an alpha form. So they've kind of given this to you already, so we can start with this first structure here. They want the alpha form. The alpha form is going to have the OH group down. So the only thing we have to do now is make sure that all the oxygens are in the right place when we draw it. So we're going to have, with this oxygen looping around, we have an OH group down. We're going to have another OH group down. Corresponding to that oxygen. We're going to have an OH group up, OH group up. So there's your CH2 group. I'm missing something. One, two, three, four, five, six, seven. Ah, okay. I see the problem, because if we're going to form a six-membered ring, we're actually going to have to That's odd. This is a seven-membered ring. Curious about this problem because they're drawing a six-membered ring here, but it's not really a six-membered ring when it attacks. It's going to be a seven-member ring because this oxygen is what's forming the bridge. So 1, 2, 3, 4, 5, 6, 7. They're only showing 6 here. 1, 2, 3, 4, 5, 6. I think this is an issue with their problem because I wouldn't say that's what you would get. I would say that you have a seven-membered ring, not a six-membered ring. So let me talk to the McGraw-Hill about this, because this is galactose. So the other option is that you get nucleophilic attack, which will displace this oxygen. But then I don't really know how you define the alpha and beta form. Because this is D-galactose here, and it has the alcohol sticking off. Oh, okay. I think it's starting to click with me now. So we're actually going to attack through this oxygen. So 1, 2, 3, 4, 5, 6. So this oxygen forms our bridge. We've still got the OH group down. So we would need this group here. Okay, so to form the 6-membered ring, we're going to get attacked from this oxygen onto this oxygen. Again, the alpha form is going to have the OH group down. Should be down beneath the plane for the second one. We'll have 2 up. And then when we rotate this, that would put the CH2OH group up as well. And then the beta structure should be that, but with the OH group up. Good, not my wheelhouse. I am not a biochemist. What's the solution? Oh, wow. Yeah, we're just going to get rid of question 12. Oh, that was disappearing from the homework sets. Next one, question 17. Which ester in the following pair would be expected to go to saponification with the faster rate? Bigger question. Well, so you're looking for electron withdrawing. So this NO2 group here is going to be more electron withdrawing, which makes this carbocation more susceptible to breaking. So my guess is going to be the top one. And that's correct. So the rationale here is that this NO2 group basically pulls electron density away from this benzene ring, making it more electron poor, which makes this carbonyl carbon a lot more electropositive. And so you're more likely to get that withdrawal. Next question, question 18. Which would undergo saponification at the faster rate? Well, okay, easiest way for me to look at this, phenol is a lot more stable than cyclohexanol, so I would argue that this is going to be more. This is less of an argument about electron withdrawing groups and more about the stability of the molecule that's produced. So anytime you're inclined to create an aromatic compound, that's going to be more stable. So in this case, phenol is just inherently more stable. Now, you can also make the argument here that the benzene ring is, even though we argue it's more electron rich because it's got the pi bonds, you could also argue that the carbons have a more positive formal charge because they've got less hydrogens bonds to them. But again, the reason I would rationalize this is that you're making phenol. Phenol is an aromatic compound. It's far more stable than cyclohexanol, so it makes a lot more sense to say that thermodynamically that would produce a more stable product. All right, question 19. We would go saponification at the faster rate. Your tertiary alcohols here, which will be the initial ones formed, they're a lot more stable than your primary alcohols. So my argument is going to be this one. We'll see if I'm right. Nope, obviously the other way. Let's see what they say. What in the world? So they're saying that one's more stable. A large terp-butyl group destabilizes due to steric hindrance in the tetrahedral intermediate in the saponification of the second compound, resulting in a... Okay. So what their argument here is that because of this big bulky group, it's harder for it to participate in any types of reactions because of steric hindrance than it is something like this. I would be more curious about the thermodynamics, but apparently that's what they're arguing. All right, amines to phenols. That was a discussion board. Let me find it. Wow, that was a long time ago. Oh, would help if I was actually looking at the right discussion boards too. So we're at the reaction screen that we convert orthohydroxybenzoic acid, aniline to orthohydroxybenzoic acid. Okay, so this is actually a named reaction that you're going to go through. I'm sorry, desktop. So we've got aniline and we want to convert to orthohydroxycarboxylic acid, benzoic acid. So the first step here, that we need to produce phenol from the amine, and this named reaction we're going to go through, this phenol will undergo what's called the Kolbe-Schmidt reaction in order to generate this compound. So the first step here is that we would react the aniline with HNO2 to give us the azo complex. This azo complex, if we react it with water, will displace and will give us the phenol. So yeah, get rid of use the diazonium to convert to the phenol. Then if we use CO2 and sodium, the sodium just removes the hydrogen to give us an O negative. It's a mechanism that is written out in the notes. Let's see if I can find it really quick. But this is what's called the Kolbe-Schmidt reaction. And I'm going to try to remember where the Kolbe-Schmidt is, but you may have to give me a minute. So the Kolbe-Schmidt reaction, if we take this, react it with sodium to give us the phenol alkoxide, this will by resonance attack the CO2, and then we'll end up getting back to the orthohydroxycarboxylic acid. And this is really the only way to get two of them adjacent. So yeah, it's just amine chemistry or diazonium chemistry. In diazonium, if we hit it with water, will give us the alcohol, and then the alcohol with sodium and CO2 will give us this. Also, Hayward projections was the other one I got asked about. Make sure I'm still sharing the desktop with you. Hayward projections. Oops, wrong discussion boards. There we go. So the Hayward projections, just try not to overthink them more than anything else. Quickest way to identify which ones are the Hayward projections. The Hayward projections are pretty much just these figures, if you put a plane through them, tilting them. So if we were to draw a line, cutting this in half, and then to rotate it. So basically the drawings here are a flat plane, and we're just going to turn them. When we finish, we should have 1, 2, 3 groups up and 1 group down. So if we look at 1, this has a CH2OH group. A doesn't have it, B does, C doesn't have it, D does. So B and D are in the running. And then because these two are cis, they should be cis in this figure. So B works, D doesn't, so 1 is B. If we look at 2, we don't have this CH2 group, so B and D are eliminated. We have 2 OH groups up, 1 down, 1 up. Here we have 2 up, 1 down, 1 down, so this doesn't work. But we have 2 up, 1 down, 1 up here, so 2 corresponds to C. With 3, 2 up, 2 down. We have 2 up, 2 down, so 3 corresponds to A. And then for 4, I mean, you can do process of elimination, but if you don't want to do process of elimination, we've got 3 that are on the same side, and with D, we've got 3 on the same side. So the Hayward projections pretty much just keep track of where the OH groups are. Now, the one of these that can be converted from this form here, what do you call it, Fisher projection to a Hayward projection, if we get cyclization, we've got these 3 oxygens that are all on the same side. This OH, this ketone group here will be converted to an alcohol. That alcohol could be up or down depending on if you're in the alpha beta form. So we're going to look for one that has 3 OH groups on the same side. D is the only one that has 3 OH groups on the same side. When this hit, it ended up being the beta form. So D here corresponds to this Fisher projection. All right, so those were the questions I had. And yeah, for 12, I'm just going to give you credit. Probably when I looked at it, I was looking for ones that gave you alpha, beta. That's ridiculously hard. Or if you're a biochemist, it's probably stupid easy. But I'm not a biochemist, so. Other questions out there? I think it's a fair rule if the instructor can't answer the question. It's probably not a fair question. Of course, the longer I teach this course, it may just end up being like there's like 3 questions. See you later, Lauren. Actually, I will see you this afternoon for the last lab. She was my only. Oh no, apparently I've got 2 other people watching. Orgo 1 following exam material questions 12 and 15. I can do that, I assume. Oh boy. So, question about the lab cleanout. Well, I'll answer that in lab today. I'll answer that in lab. All right, let's bring up question 11. Not question 1, question 11. So the synthesis of 1-butene from ethylene and ethanol. I will never stop being annoyed with the fact that these arrows are written in the wrong way. So we're going to take the ethanol and make, oh, that's pretty straightforward. So typically what we're looking at, yeah, it was trying to make me do one. So for 11, typically what we're looking at, particularly with a lot of alkyne chemistry, is getting rid of this hydrogen to make it a good nucleophile. So off the bat, I would say A is going to be our nucleophile. If we hit ethylene with, or ethine with sodium, we'll end up extracting a hydrogen. This will make a good displacing group. So I'd say that's probably it. Yep. And then it's just nucleophilic substitution. So if I had to pick one, I would definitely say bromoethane would be the most likely choice. So this negative here will attack the bromine, displace it, and we'll end up getting the final product. So now the way we make the ethine sans the hydrogen is we're going to start with the ethine. And then to make the bromoethane, we're just going to use ethanol. So this is the overall step. We're going to take our ethine, convert it to the sodium form, take our ethanol, convert it to bromoethane, and use nucleophilic substitution to give us our final product. All right, now how we actually do it. Synthesis of butane from ethine. Come on, reagents. Oh, what? Super confusing. E, I would say, is nonsense. What? Synthesis of 1-butene from ethine. What is the context here? Let's try C. That seems to make any sense. I'm assuming they're meaning you're trying to convert this to the sodium form, which in this case, the sodium azide is the best reagent. None of these are bases. So yeah, I'd agree with that. And I'm guessing it's asking how you would convert the OH to that. Halohydrogen is C, that won't work. Hydrogenation B won't work. Br2, FeBr3, this is more of an organic 2 reaction. This is how you brominate a benzene ring. Sodium bromide and water versus PBr3. My first guess would be PBr3 because I know that this is selective towards converting an alcohol, and that seems to be their attitude. You could use sodium bromide and water. It would just be prohibitively sluggish. So there's your step, PBr3 or HBr to react the ethanol to bromoethane, and then your sodium azide would react off that hydrogen, which would, the end products would react with each other to give you the final product. All right, question 15. Ooh, another synthesis wrong. So we're starting with a molecule on the left, this 3-methyl-1-butene, and we want to convert it to 4-methyl-2-butene. So if you look at it, 1, 2, 3, 2, 3, 2, 3. We're going to need to add an extra carbon. So the starting molecule here is 1 carbon less than the final molecule. So my best guess is that we're going to form a terminal alkyne, and then we're going to use our terminal. We're going to react our terminal alkyne to remove a hydrogen and use that for nucleophilic substitution. So a good intermediate, I would say, is compound E. What we can do is we can extract a hydrogen off of this and then use nucleophilic tack on something like CH3Br and end up with the final product. And it agrees with that. Now, the way we would make this is I would start with definitely something like B, a double halogen, and we'll see how we can convert this directly. But basically, if I take this 1,2 dibromo complex, I can make it from the starting alkene here just by reacting it with bromine. So this is easily converted made from the starting molecule. Yeah, how do you make the starting molecule? You just take that. So this is the overall conversion. We take our starting alkene, react it with bromine to give us the dibromide, use a very strong base like sodium azide to give us the alkene, and then use another strong base to protonate that hydrogen and attack something like CH3Br. All right, so the reagents to go from this to this, Br2 is going to work perfect. To go from Br2 to the alkyne, sodium azide, not going to work. This is where it gets a little tricky. So there's NaNH3 and then there's NaNH2. And I think it's A. I don't remember off the top of my head. Let's see. Nope. So NaNH, oh, that's right. Okay, it's coming back to me. So NaNH3, this is used to convert an alkyne to a transalkene. You want two equivalents of NaNH2. This is a strong base. These strong bases are powerful enough to take your two halogens and abstract them to give you the alkene. And yeah, I get them confused. The NaNH3, it's weird because NaNH2 is made by mixing NaNH3 together, or at least that's why it's confusing for me. In the case of sodium, the reason why we're using the sodium to generate the transalkene is that it basically goes through a free radical mechanism. All right, now the last reagent to go from this compound here on the right to this one, I would say first we're going to want to remove the hydrogen. And then we're going to use something like CH3I. Now we're going to want a really strong base to make sure this happens. It may consider sodium hydroxide, we'll see, but definitely with CH3I on its own, it won't do anything. That won't do anything. That'll give us an alkene. So let's see. Yep. So yeah, C, I don't think an alkyne is basic enough to react with something like sodium hydroxide. Definitely like something like NaNH2, it'll definitely react. So yeah, I hope that helped. Good synthesis problems other than 11, which was just kind of poorly worded. Good question, it's just poorly worded. Yeah, you're welcome. Do we need to know how to name something that has an OH group, a triple bond, and a double bond? No. That's just kind of on the extreme case. If you can name that, you can name anything on the final exam. So there are questions about naming alkynes, alkenes, alcohols. They're rarely put together on the same question. We joke among the organic faculty that generally when it starts getting that complicated, there's probably a trade name.
So yeah, if it's got a, I mean, they do exist. Like I do put practice problems on the packets just for that challenge, so you can see like there is a pattern. But definitely nothing like that on exam. Those are ridiculously hard questions because it's like alkene, ine, it's like hydroxy, ene, ine, something like that. And the alkene takes priority. Alkyne takes priority over the alkene. So you number it so the alkyne comes first, then the alkene, and the first number in front of it is the alkyne, the second number is the alkene, and then you do a hydroxy for the alcohol. I mean, there is a pattern to it. It makes sense why it is what it is. But it's a lot of work for a molecule you'll probably never deal with. Yeah, it just ends up being a series of rules. It's interesting that the rules do exist, but you're never going to encounter a compound that you had to name like that. Again, if you do start getting like weird polycyclics and things like that, it's probably going to have a trade name. IUPAC was a nice idea. So every now and then I get bored and I do ham radio, and I'm kind of fascinated. I'll go to eBay and I'll look for radios. Just out of curiosity, that's where I got mine from. I've got a pretty good deal on the one I'm running right now. But I'm always kind of fascinated because right now there's like a wealth of these really antique radios out there, and people are asking for a lot of money. Like this Heath kit, they want $235 for it, and the thing is running vacuum tubes. Like there's a vacuum tube, there's a vacuum tube, there's a vacuum tube, there's a vacuum tube. All these are vacuum tubes. So for $235, they want something that really the only thing you can do with it is just kind of listen. You can't really transmit anything interesting. This is a Swan 500 transceiver. They want $145 for it. That PA plate, PA grid is also referring to the vacuum tubes that are inside this thing. Like there's a tube, there's a tube, there's a tube. Tubes are like $100 a piece to replace. Somebody wants $175 for this sucker. It's not a vacuum tube one, but it only does like Morse code and maybe a little bit of single sideband, although it doesn't say if it's upper or lower. And I think it's hilarious because on this exact same website, you can buy a cheap Chinese radio, completely digital, for $155. That will probably do just about as much. I'm just fascinated because I'm wondering like how many hundreds of dollars I could get for my radio, which is not a bad radio. It's actually a pretty good radio, but I mean, I got lucky because I think people just weren't paying attention when they started bidding on it. Yeah, I'm always just fascinated with what people think they can get for some of these things. Like it uses vacuum tubes. Those haven't been around since the 70s, 80s. Question 22 on the Orgo homework. Draw the major product isolated from the reaction 1 hexyne with aqueous sulfuric acid, mercury sulfate. I feel like this is a named reaction. All right, let's start with what we have, 1 hexyne. Hex for 6. 1, 2, 3, 4, 5, 6. Why do you do this to me? I'm willing to guess what you get here is a ketone. So the initial product you should get is you add water to the double bond to begin with, and you end up producing what's called an enol. So Orgo 2 students already know what an enol is. They actually have a whole unit on it, but an enol here is when you have an alcohol attached to a double bond. And what ends up happening is your double bond will actually tautomerize. The hydrogen will go over to this carbon, and you end up moving the double bond around, and you end up getting a ketone. So that's my first guess here, is that you're producing a ketone. 1, 2, 3, 5, 6.
So yep, this is just hydrolysis of an alkyne, and this is the big difference. This is one of the few reactions. So I talk about in the notes how an alkene and an alkyne, the alkyne is just the alkenes to the extreme. For halogen addition, they just add twice as much. When you do hydrogenation, you add twice as much. But the big difference between them is hydrolysis. So with hydrolysis of an alkene, you get an alcohol. With hydrolysis of an alkyne, you actually get a ketone or an aldehyde depending on the ketone you're working with. And this is something that shows up when you do the first synthesis in organic 2. You synthesize diphenylhydrazine. So diphenylhydrazine is sorry, not diphenylhydrazine. You start making diphenylacetylene. So you make that compound from trans-stilbene, which is this compound here. So in the lab that's done, you take this compound, you take your starting compound and you heat it. After you make this diphenyl acetylene, there is a reaction that students are told to run, and what they have to do is they have to take their compound and they have to heat it in the presence of water. So if you take trans-stilbene and heat it in the presence of water, you get this compound. So you get 1,2-diphenyl methanol. In the case of the alkyne, you get this compound. So you get 1-phenyl-methyl ketone. And the big difference here is that this alcohol here, if you hit this with Jones reagent, this will react, but this won't react with Jones reagent. This will react with 2,4-diphenyl nitrohydrazine. This one won't. These are compounds that are covered in organic 2. So we can use this difference in reactions with water to distinguish between an alkene and an alkyne, because if we hit both of these with bromine, they're going to absorb bromine. So we can do a saturation test with bromine, which is what y'all have done in organic 1, react it with bromine in carbon tetrachloride, or bromine in methylene chloride, and if you see the bromine color disappear, you know that you've got double or triple bonds. But how do you resolve between an alkyne and an alkene and an alkyne? Well, it's easy. Heat both of these up in acidified water. If you have an alkene, it'll form an alcohol, which will react with Jones reagent. If you have an alkyne, it'll react to form a ketone, which reacts with 2,4-dinitrophenylhydrazine. So yeah, this is actually a really useful reaction to exploit if you're looking for a qualitative test as to if you have an alkene or an alkyne. The bromine test will tell you if you have unsaturation, but the reaction with water and the subsequent product that forms will tell you if it's an alkene or an alkyne. And if you're unfortunate, you got both, but we don't bother ourselves with those types of problems. Yeah, long story short, when you hydrolyze an alkyne, you actually end up getting a ketone or an aldehyde depending on the alkyne, but you always end up with that carbon-oxygen double bond. Question 23. So it should just be a syn addition across the triple bond of hydrogen, since 1 mole you would be left with a double bond. Draw the and the question is draw. I guess I can bring it up for you. Draw the major product of isolated reaction of 3-hexyne with hydrogen 1 mole in a Lindlar catalyst. So yes, it's a syn addition. So we start with 3-hexyne. 2, 3, 4. And do the triple bond. So actually, these are pretty straightforward. So if we have 1 mole of hydrogen, we're only going to do a single hydrogenation. And you'd be left with a double bond. And when it comes to Lindlar, you actually, so Lindlar is a poison catalyst. I mean, I'm sure you know this, but anyone listening. The Lindlar catalyst is a poisoned hydrogenation catalyst. It can't go beyond hydrogenating an alkyne. And with Lindlar, we always end up with a cis product. So when we finish, we end up with this structure. 1, 2, 3, 4, 5, 6. So we get the cis, and that's your product. Yeah, it's always cis with a hydrogenation catalyst. It would be fun to see if there was a reaction we could do where you would actually like, because the nice thing about hydrogenation catalysts is they do that have that stereoselectivity, and so you could actually in principle create chiral compounds. You could take something where like there's a methyl group and you hydrogenate, you just get like the R form or the S form. The drawback is hydrogenation is a lot more dangerous than what the book implies. When I did organic 3, we did hydrogenation. Actually, we had rubber septa on the reactors because if any oxygen got in there, it immediately ignited in the presence of the hydrogen and actually had that, to the group behind me, we heard the septum blow off and shoot to the ceiling. Little rubber septa bounced around, but yeah, it's great that your book says here's hydrogenation. Hydrogenation is super dangerous to do in practice. On top of that, we don't have a polarimeter. We've looked into getting one. It'd be awesome if we could do a lot of that, do polarimetry. We just can't seem to find one that would be meaningful. But yeah, Lindlar catalyst, super stereoselective if that's what you need. All right, so we're pretty much at the time limit. Again, if you ever have questions, please feel free to email in advance. We actually only have 2 more live streams. We've got the one Friday and we've got the one Tuesday. If you are interested in having a live stream during the exam period, if several of you want to get together, shoot me an email what times work best. I would prefer to do this for when I know at least 3 or 4 people are going to show up, not just kind of like on the off chance. When I do get the time set up, I'll send out an announcement with a link and the date and the times. Wednesday afternoon, particularly after 11 o'clock, really isn't going to work. For that first day of exams, I need to actually start prepping for summer, so I'm going to be kind of out of commission Wednesday. But definitely Thursday and Friday and following Monday, those dates are still pretty open. Only going to do 2 just for convenience. Otherwise, everyone's going to want a private session. You're always free to reach out by email. You're always free to see if there's another way of contacting me. The other big thing is that next Tuesday is the last day of a regular class, and then Wednesday is the start of exams. So it's Wednesday, Thursday, Friday, Monday, Tuesday for the exams. The final exam opens up that Wednesday. You have until the following Tuesday at 5 p.m. to take it, to have completed it by 5 p.m. Tuesday. There are no extensions beyond the 5 p.m. Tuesday because the school is literally closed. That is the end of the semester. You cannot get an extension without claiming an incomplete. I'm going to tell you personally as an instructor, incompletes are massive pains to deal with. So I would recommend you take it Monday or earlier for the final exam. Tuesday, I'm going to be kind of compiling grades and submitting grades because they want our grades by 5 o'clock. If you take the exam Tuesday and you start having technical issues, particularly as we get past noon, I'm probably not going to grant you an extension because there's really not much I can do for you. Saying that, well, I waited until Tuesday and then I had computer issues, that doesn't really warrant an incomplete. So please take it Monday or earlier. You have the full weekend to take it. If you have any issues, and you can email me. Now, the discussion boards, I told you, throughout the semester, you're free to complete them again for as many points as to get all the points back. That said, Wednesday morning, I'm going to come in and I'm going to finish all the discussion board grades. So any outstanding discussion boards are going to get graded probably Monday and Tuesday. After that, I'm not grading anymore. So I kind of need to start putting a cutoff on your homeworks. I need to start putting cutoffs on your discussion boards because, again, Tuesday afternoon, I have to submit your grades by 5 o'clock. If you're still trying to submit discussion boards throughout the exam period, that's just going to create more headaches for getting the grade submitted. So Tuesday afternoon, practically Monday morning, that's it for discussion board revisions. You need to submit them. They're done. That's the only chance you get. Again, I'm going to keep grading them here, but after Tuesday, if you submit anything for the discussion boards, it's just not going to get graded because it's late. Other than that, that should really be about it. So I will see some of you this afternoon, but we definitely have live stream Thursday, Friday. I'm sorry, we got 3 more live streams. Thursday, Friday, and Tuesday of next week. And any that I get emails about, I can create 2 more if people kind of wanted to review session. All right, thanks for showing up.